Hello once again, everybody. Welcome back to another Scratch Built OS stream. So, today I'm going to try and finish the first pass at the heap allocation because it's not been working perfectly. If you saw the title of this stream, I hope we'll finish it. And then there is something else I'd like to do also. I would like to see if there's a way I can actually print debug information to the terminal that I'm running the emulator from. So when I do a run, let me show you. So here's our output so far, but it's actually being run out of a PowerShell window right here. And I think there's a way that I can have my emulator program, which is Kimu, dump info to the console that it's being run out of, which would be really useful because then I can arrow up and down. Because the only problem with this is that I don't have arrow keys to arrow up and down. So as I'm printing stuff out, as it scrolls down the screen, it just erases the stuff above. So I can only print up to 25 rows of usable information before it starts getting wiped off the top of the screen. And if I just, instead of printing stuff to the screen in the emulator, if I just have it dumped to the terminal that's being run out of it, then I can actually scroll back through and see stuff. So that would be really useful. But I want to do that in a more C++y way using a nice class, making like a debugger object class and making it a singleton, which requires us to have the heap fully working for new and delete objects. So mostly, it seems to be mostly done. The only thing I'm not able to do currently is I'm not getting the merging of free memory blocks working. So if you've been following along, you'll know that I implemented a linked list kind of idea for the heap, and it keeps track of whether or not a block that's been allocated is either being used or is free. And so what it should do is every time I free a block, that block should then look to its neighbor blocks and see if they're also free, and if they are, merge together with them so we get bigger blocks that can then be subdivided back down again, so we don't keep splitting off the end of the heap and getting a whole bunch of tiny little blocks that are impossible to use. So this screen that's being shown right now is the result of this code right here being run. And it's just exercising the malloc and free commands. And what should be happening, I believe anyway, is it does some allocations of these specific sizes, and then it does some freeing. But at the very end of all of this, the amount of the heap should be back to the original size, which it's not. See, because what I have printed out here is these numbers on the left are the amounts of bytes getting allocated and freed every command. So there's a before and after. Well, it says before the merge or before the malloc and after the malloc. So we're mallocing 78, and this is the amount of heap we have actually. So this is saying before a malloc of 78 bytes, we had this much heap. After a malloc of 78 bytes, we had this much heap. And the same thing for frees. So before a free of 64 bytes, we had this much. After a free of 64 bytes, we have this much. And then I've got it printing out when it actually attempts to do a merge of free blocks. And so something is wrong here with after the merge. See, so first of all, it shouldn't have actually done a merge at this point because it can only merge if the block that I've just freed has adjacent free blocks after it. And I've very carefully set up this experiment here, this sandbox test, to free things in a specific order. So first, it does a malloc of size 30. So there's a block of 30 there. Well, actually it has a minimum of 78 bytes. So if we're mallocing less than 78 bytes, it'll just allocate 78 bytes. If we do more than 78, it'll do the size that I asked for, but there's a minimum size enforced. So the first one is below the minimum size, so it does 78, and that's the first chunk. And then we allocate above the minimum of 90, so 90 plus there's a header on top of it, so that goes to 104. So we allocate that. That's the next block. And then we free the first block. Hello, Mollymock. Good to see you. Thanks for joining us. You gotta put in someone to wave to. Yes, you did it all. You did it all wrong. Like that. I could just change that to like wave to say waves at everybody. I don't know. What's up? Want to see my fancy? Want to see my fancy schmancy splash screens? I'm a real streamer now. Very fancy. Okay, so what was I doing here? Oh, right. Yeah. Fixing the heap block merging. Yeah, so I have it allocating a specific chunk first, and then another chunk next to it, and then freeing the first chunk. So that first chunk should then look to its neighbors to see if there are any free ones. And there shouldn't be, because the first one is at the start of the heap, so there's nothing above it. And the block next to it is being used still, so that block should just kind of sit there on its own. Yet, it says it's merging, or attempting a merge, which is wrong. Because then after that, I allocate another block on the end, so we have 3 blocks plus the rest of the heap, and then we free number 2. So block number 1 was already freed. Now that we've freed number 2 should look to its left and right to see its neighbors, and it should see that block 1 is free, and then should merge with that one. So that's what's happening, why it says merge right here, so it's trying to do that. And then I free block number 3 again, so then it should look to its 2 neighbors, and it should see a big merged free block there and the free rest of the heap, so then it should merge, and then we're all back to the original then, so the heap should be back to what it used to be. But it's not. See, so we had 1637 bytes to start with. Now, at the end, we're at 16342. These 2 numbers should match, though. In fact, let me draw this out a little bit. I have a fancy new method here. Watch this. Oh, sorry, wrong one. There we go. There we go. Okay. So here's memory. And when we create memory, we section off a little bit at the top to be the very first header. And in that header, there is a little spot that says, okay, where is the next header? So it points forward to the next header. And recently I've also added another piece that has a point back to the last header. So from any block we can go forwards or backwards because we know where the last one is. And then there's a spot to denote whether or not the block is currently being used or not. So like that. And there's a spot to denote the number of bytes that this block represents. So at the very beginning, the heap looks like this. It's one header at the top and the entire free portion of memory. And that the number of bytes that are in that is stored in this one right here. That contains the number of bytes. So then, at this point right here, oh, let me go back and show you. So, at this malloc command right here, we will section off 74 bytes. We'll call that. And then make a new header at the bottom. Right? Actually, hold on. There we go. So it's got the number and the pointer back. So now, this field right here, see, I asked for, it'll give me a minimum of 64. So now this section right here is 64 bytes long. This variable right here will be pointing to this spot right here because it's the next spot in memory. Okay? And then this next one right here, this malloc of 90, that creates another section. So we'll go to the bottom header, which is this one right here, and then say, okay, from here we're going to section off 90 bytes. And we'll say that's bigger. That's like this right here. And then from there, create another header at the bottom. Like this. With its pointer forward, pointer backwards. Oh, I forgot. This header right here also points backwards to right there at the beginning. And it's not being used. Oh, this is all being used now too. So this first section of memory is now being used, and it's 64 bytes long. This second section of memory is now being used, and it's 90 bytes long, right here. And this last section is the rest of the heap long, like that. And this header then points to this header points to this header. So if we drop in at any header, we can now go forwards or backwards to the next one. And so then, what I do, the next one, this free, we free number 1. Alright, so this is, go back to the, so this is number 1, this is, oh gosh, so that's not very legible, there we go. That's number 2, like that. So then we go back and free number 1, and all we do is say, okay, this is no longer being used. Okay? And so then when we do that, it should look to its neighbors. So it jumps forward to number 2, and then looks right here to see, okay, is it being used? Oh, it is, so I can't merge with that one. And because this is the first one, there's nothing to point backwards to. It can't do anything about that either. So this block will just sit there. It should not merge anything because there's nothing on either side of it to merge with. Then, oops. Then we do another malloc of 50. And that's below the minimum, so it'll do another 64. So then, oops. I'm getting used to my buttons. So then we'll go through and say, we'll look for the first open... Oh, maybe this isn't working the way I thought it was. Because when we ask to allocate new memory, we'll traverse the list to see if there are any already allocated blocks that aren't being used. So we'll actually start at the top right here and check, is it being used right now? No, it's not. And then I think actually what's happening is because I've allocated less than the minimum size, it'll just use this. It'll just say, okay, this one is big enough, so now we'll just switch it back to being used, and it'll equal that. So I think maybe what I have to do to force this to use new memory is make this bigger than the minimum size. So what if I go to 130 right there? Because then what that will do is, because this one was already allocated to be size of 64, that's too small. So it'll say, oh, this is too small. Even though it's not being used right now, it's too small, that's fine. We'll bounce on to the next one. Oh, this one's already being used, so we can't use that one. Then we'll bounce over to the next one, which is now going to be num3, and say, oh, I guess we'll just have to split something off new. So it'll do that. So now we'll just make a new header like this. Change this number to now say, this is now 130. And it's now being used. Like that. Okay? And there's the memory right there. Okay? And then we get to freeing number 2. So now when we free number 2, all we do is we go in here and say, you're not being used right now. Then when that happens, we will look to our neighbors. Oops, let me draw our neighbors in here so these are linking back. We will look to our neighbors and say, starting from right here, we will jump back to the first one. We'll go this way and say, okay, are you being used right now? We'll go look here and say, oh, you're not being used. That's great. Okay. And then we will jump to the next neighbor down, which is from here over, and look and say, are you being used right now? Oh, it is right now. Let's not worry about that one. But we did find 2 adjacent unused blocks right here. So then what we'll do, we'll take the one above us that was not being used and change his neighbor to the one below us that is being used. So instead of having this, we now jump him all the way over to this and get rid of this. And we change the back neighbor here to go all the way over here. So effectively, we have just basically nixed this header. Oh, and we need to change the size here to match the rest of this data now. So eventually at the end... Oh no! Dang it. There we go. Eventually in the end it'll look like this, because we have just merged the blocks that were in here together, and now we have a much bigger spot of memory all at the top, ready to be reallocated. And then the very final thing is we do a free on number 3, which will do the exact same thing. So we look at block number 3, right here, and say, okay, you're no longer being used. And we look to our neighbors that's not being used. So we look this way. Oh, it's not being used. We'll look back this way. Oh, it's not being used. So then we get rid of all these and point this guy all the way to the end, because this guy was pointing to the end. And then we point this guy back to nothingness because it's now at the end. So in the end, after everything, all this should go back to what we originally had, which was our original heap size. Right? That's very complicated. But makes some reasonable sense, I think. Alright, so now that I've changed this number, I think that'll make it work more like I expect, so let's see what happens. No, that didn't do anything. See, we still did a merge here first, after the first free, which we should not have. But I think I might actually have an idea as to why. So in Memory CPP. This right here is where we merge neighbor blocks. So header next is pointing to the beginning, starting where the header is. So like every block, has the pointer to the next and the pointer to previous. So the data contained inside this variable points to just before when the block starts. So that is before the header. Because what I was worried I was doing was accidentally pointing it to after the header and then trying to interpret this next portion as the header, and the data inside there's all messed up. So it could be confusing it. But I don't know if that's necessarily the case. What do you think of my whiteboard drawing setup? And we also have 3 cases when we can merge. Because we have the block we just freed, and so there could be the case where the previous neighbor is available, but the next neighbor's not, or when the next neighbor's available and the previous is not, or when both neighbors on either side are available. And so we want to do it all in one step if possible, or as many as possible. So I actually kind of diagrammed out the 3 right here. So this is the case where both neighbors are free to merge. So the current one is the one we're on, so if both neighbors are free, we'll point the previous one to where the next one was, and therefore eliminate all of these headers inside, thus making one big block. Oh, yeah. So we do need to update some data too. So we can't just change the pointers. We also need to change the size that the surviving header at the top says. So, like, if we're... So getting used to this. So if we've got, like, our 3 headers, and this top one here is the one that's the top free one, and it says how big it is, pretend it's like 64. Let's say all these are 64. Like 64. If we merge this block and this block together, this number that it says it's responsible for now needs to become 128. Well, actually, no, because plus the size of how many headers plus the size of a header, because this data right here is 64, and this data right here is 64. But we're also absorbing a header inside it, which I think is 18 bytes or something like that. So this was 64. But when we merge these two together, we need to say we're absorbing the 64 plus the 14 plus another 64. So that's like 142, I think. Something like that. So now this header and block is 142. And I'm not doing that. All I'm doing is just changing... Yeah. Sure. Because originally, this guy's pointing here, this guy's pointing here, this guy's pointing here and this guy's pointing here. Originally, all I was doing was just changing where these arrows are pointing. Like this. And just pointing this guy way over here. And pointing this guy way over here. But not updating the number. So that would confuse the allocator when it searches for blocks to use, because it tries to reuse blocks that are already allocated if they're big enough. But if not, they'll move right along. So if I don't update the number, like if this guy... Oops. If this thing here still says 64, but there's enough space here to be that 142 or whatever, but if this guy isn't updated correctly, the allocator will just move on to the next one because it says it's not big enough even though it is. So I need to make sure to upgrade or update the number. Whenever we merge blocks. So this is the case right here. Oh, wait a second. I think where we actually had another problem too. There's a problem before that where we're not actually getting into either of these cases. Because the first thing that it does is it just looks at either neighbor and checks to see if it's in use or not. And then decides what to do based on that. And I've got print statements in here, you see? And as you'll notice, they're never getting printed. So like this printf merge, where it says merge, that means it's getting into the merge neighbor blocks function, but it's not actually doing any merging because either of any of the three cases depend on at least one of the neighbors not being used at the moment, and they both start out saying that they're being used, and so therefore, see, I've got more print statements in here: merge across, merge up, merge down. None of those are being printed, so therefore we're not getting into any of these. So why is that? So the check that it does here, it first checks to see if the current variable that we're freeing, if either of his neighbors are null pointer, because that means that it's either at one of the ends. So that is to say, like, if we're at the beginning right here, we can point forward, but there's nothing backwards to point to. So this data right here will say null pointer because there's nothing to point back to. So if the current header previous is null pointer, that means he's at the beginning and don't bother looking back. And if the current header next, which means the next one, so that would be this one right here, is null pointer, then don't bother because we're at the bottom. So this one down here would actually have null pointer right here because there's not another header to point to. So that would mean he's the last header in the list. So if it's on either side, you don't need to go looking farther up that way because there's not going to be anything there. So the thing is, when I allocate number 1 here, he should have null pointer as his previous because he's at the top. So he should not hit here. But his next should not be null pointer because we have allocated number 2 right after him. And so his next pointer should point to number 2. Huh. So why would it not be? I guess I need to figure out what... I'm gonna get rid of some of this for right now because we don't need it. I just gotta figure out why. So we'll just deal with number 1. Let me make all that again, see what happens. Yeah, so we're still... How much should I allocate to start with? Yeah, so the header is 14 bytes. So, because we started out with a heap size of 16384. And so, because of the header at the top, we start with 16370, which makes perfect sense. That's minus 14. So then, is the allocation actually working right? So 16370. Wait a second. Oh, is it making an extra header? Minus 78. That's not right. We have 16292. This says it should be 16296. What I'm afraid it might be doing, actually, is it might be making a header right here next to it. Because what it's supposed to do is supposed to start looking and see, is there a free block available first? So, like, this is what the heap looks like at the very beginning. There's nothing allocated, so this should say I'm not being used and I've got the whole heap available to me. So that's what, 370, like that. I don't point to anything, and I don't point back to anything like this. So it should look for a block already allocated, which means there's a header at the top. So it should find this first header and say, oh, are you big enough to hold what I need? And it'll look here and say, absolutely. So it should just allocate the size that I've asked for, which is... And it shouldn't need to allocate a new header is the thing. The fact that it's... The fact that it's counting the header in there should not need to happen. So what I think is actually happening, it's making another header right next to it, which should not happen. Instead, it should just go out the 64 bytes and make a new header down there, like that. And then change this guy to say, we're 64. Oops. No. No. There we go. We're 64 right here. And then this guy should be the rest of the heap, which is the 19266, I think is what it was. Oh, whatever, 19296. So why would it not be... It's not subtracting, right? So where it decides if there's a block that it can split is right here. should just be reusing the same header, though. Did I calculate that right? We started with... how much? 16,384. So, minus the 14 bytes for the header, the first header. That's the available heap we have to start with. Which is true, because it says so right there. Oh. And then so... so here's where it sets the size, and size is... well, it's just that's not total allocation size, though, is it? Hold on. Where'd it go? Yeah, size just equals minimum block heap. So it should only be allocating a minimum of 64, not another header. Yeah, so 64 plus 14 is 78. So that whole chunk is a header plus the data. Math. Because these two numbers should only have a difference of 64 bytes in them. Oh, no, it shouldn't, because it took up a header after that, too. Here. So... here, let me show you. So, it starts out like this. Unused, and has the entire heap inside it. Which is the 16... shoot. 384. Right? And so then I ask it for 64 bytes. So it goes from right here, it moves down 64 bytes, and then makes a new header of 14. So it changes this guy right here. No. To 64. Says he's being used. Oops. Then changes this guy. Says he's not being used right now. Sets the 2 pointers so they can get back to each other. And so it would be 78 minus. So that minus 78. 16292. Is that what we ended up with? That is what we ended up with. Okay, never mind. So that's working. So after our first malloc, we ended up with that. And then we free it. Here, oh, you can't see. Let me show you. So right here. So we had the whole heap of 163870 minus 64 minus 14 does take us to 16292. and then we free that same data. So all that does is just we go and say we change the in use to not in use. Okay? And then the merge should go through and say, look to both sides for neighbors to see if there are unused blocks. It can't look backwards, there's nothing there. But it can look forward to see this header right here. And it'll say, oh, it's not being used either. What's the difference between minus what we end up with? This weird number here. I don't understand that number. 3, 5, 6. That's exactly 64. Oh, is it because we're not counting the... Oh. It's because the header still exists. So for some reason the merge process is not going through. And when I ask for how much heap is available, it does data excluding the header. So it takes this, whoops, and this. So if we yeah, because if we do, oh, let me put you back here. So if we do 1, 6, 3, 5, 6 plus another 14, that puts us right back in. Yeah, so 14, that's the size of one header. So that's because this header is still in here. So it's not getting counted in the total freeing. And so what the point of the merging is supposed to do is to get rid of that header, essentially, and therefore make it be counted in the whole size of memory again. So, to give it that. Okay. So that makes sense. So the numbers add. So now I got to figure out why the fudge we are not correctly doing the merging. Did you leave, Mock? Are you still there? So why neither of these are getting activated? Because these right here, this is what... Am I quiet? Oh, I see. Okay. I got it. Thanks. So I gotta figure out why neither of these are getting fired. Just out of curiosity, I'll do another quick if. So if no header next, and is there a reason that they're both null pointer for some reason? Current header previous. Ah, man, I cannot spell. Bad. Oh, So look, it printed bad. So for some reason, both the front and back pointers are null pointer for some reason. That means it's not pointing anywhere. So how... Oh! I know what it is. I think I am having the problem that I was originally thought I was having, where I'm actually looking right here rather than right here at the beginning, and then I'm trying to treat this spot right here as the start of the header when it's not. So see right here, when I do a free, I pass it a pointer, but the pointer here is pointing to the beginning of the actual memory and not the actual header. So I'm taking this location, and then right here saying, that's a pointer to a header. When it's not. So it actually needs to be location minus size of heap element header. Because we want to go back that amount to get to the start of an actual header so we can actually read the data out of it appropriately. Must be a pointer to a complex. It's a void pointer. Oh, do I need to do that? Yeah, so now we'll take the location that we passed in and subtract off the size of a header, actually, to move us back to the beginning of a header, and then treat it like that. Ah. There we go. Okay, that's not quite right. So there we go. So we got into one of our stops. Got it. Okay. So, what do we got here? So all I'm doing is I'm allocating one variable and then freeing it immediately. So what that is doing... Battery looks fine. Oops. So, 16370. Okay, so that's what we have to start with. And then after we do the first malloc, we create a new header, blah, 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 like always. This is the rest of the data, whatever it is. This guy becomes 64. We change him to being used. This guy's not being used. And such and such. So then when we free this one, then we look to the neighbors. So we first look backwards. He doesn't have any neighbors backwards, though, so that's why we hit... stop 1, which is only if... That's why we didn't hit stop 2. So stop 2 would only get hit if there was a previous neighbor. He's not, because he's the top of the heap, so that's fine. But we did hit stop 1 because there's another header to go down to, which is this one right here. So, because this guy is successfully pointing there. So, we found this guy, and then when we freed him, we set him back to being not needed, and then looked at the neighbor to say, hey, are you not being used? Hey, yeah, you're not. Let's merge you two together. And then so, that's why we have a merge down right there, because this is in the case where... Yeah, this is this case right here. There's no previous neighbor to use, so we're taking ourself and overlapping the next header. So we're merging down and not up. So the only thing that is totally wrong here is the size of the heap afterward. And that makes sense, because that is we are not updating the number. So, let's just use merge down for right now. So in merge down, in addition to changing where the pointer is pointing to, we also have to do current header payload size. Hey, I4T. Thanks for the follow. Where was I? Oh, yeah, so we gotta set our new size to plus equals current header next payload size plus the size of the header that we just absorbed. Heap element header, there we go. See, so it says the biggest size is now 64 because we didn't do the addition to merge the sizes together. So what in essence happened... Oops, let me show you. Is this guy right here... Arg. Whatever. This guy right here, this guy said 64 originally, but then when we did the merge and got rid of this, we didn't update the size. And so when I ask it for the size of the whole heap, we're still just returning that out, 64. What we need to do is change that number back to what we had originally, which was 64, plus the size of this header, plus whatever this guy had in his payload, which is the rest of the heap. So, theoretically, now that I've just done that, with this right here. Nope, not that one. This right here. We should see it, the number's right. Okay, no, that did not happen correctly. That is not, that is not what I was expecting. Why not? So, what did I do wrong here? Oh, I need to get it. Oh, I did these in the wrong order. So this line right here essentially deletes a header from existence because I change where I'm pointing to the next header to pointing over it, and we'll never get it again. So I need to get the data out of the header I was pointing to first before overlapping it. That... Oh, because I didn't save it. Silly. Save stuff first. Look at that. There we go. See, so we allocated something, and then we freed it, and we got right back to our original heap size, which is exactly what I expect. Okay, so now I gotta try this with, oh, I gotta do that for these other options here too, theoretically. Oh, but I gotta change it here. So we want to do. So this was the case if the neighbor is below us. So this case here is if the neighbor is above us. So we have to use the previous. So we'll have to check that here in a second. And then this case here is if they are both... If both neighbors are free, so we have to add them both together. And so because the previous is the one that's surviving, equals current header. Oh, someone messaged me on Discord. Hang on. Oh, I just got a Discord chat saying someone's actually trying to run this. Or run the build. Let me answer him real quick and see. Just do it on Discord up here. That seems to be the problem. Real-time debugging. So he says I was trying to run Twilight custom Twilight OS, but make build runs with errors. So I asked, well, what's it complaining about? He says he's going to take a screenshot real quick. I'm going to take a screenshot real quick. NASM. PPT. Oh, not found. Okay, here. I'll go ahead and show you. So he's trying to do... Oh, I know what the problem is. He's trying to... So the build process uses a stripped-down GCC compiler for CPP files, and it uses NASM for assembly files, and it looks like he doesn't have NASM installed. Yeah, so NASM is the assembler that turns assembly files into object files, and then GCC is what turns CPP files into assembly or to object files, and then they're all linked together. Because I've got CPP files and assembly files. Yeah, so I linked in the README file on the GitHub page, I linked the tutorial on the osdev.org wiki website about how to make the cross compiler. It's the bare bones simple one, and I'm pretty sure it said get NASM installed in there. But if not, I need to actually make that a note on the README somewhere. says he installed it. What group is this guy from? He DM'd me specifically on Discord. I'm in a couple of groups. I'm in a couple of like programming related groups, but I don't know. It doesn't say how I know him from. I've never actually had anyone try to build and run it that I know of, so this is really cool if he's actually going to get it to work. So I'm going to ask him, does it actually work? Still says shortcut inside the OS folder. Yeah, he still says it's the same error. Still says it's the same error. He's on Windows. He says he's actually using Windows, but he has G++, GCC, and GDB installed. And he says he just installed NAS. He must have Make installed too. Because he's trying to run the make file. So he says he put a... So it's really optimized to work for Linux because Linux adds things to the path automatically. But what he could try doing is, in the make file, change all the paths to absolute paths for Windows. Maybe that would work. Yeah, so he could try to, well, here, let me show you. The make file is here. So, and right here, I specify what the compiler is. So this is a special version of GCC and a special version of G++. And then the assembler here is just NASM. So what he could do is change these here to have the absolute path to where he installed. From, yeah, so I'm going to ask him, are the compilers added to his Windows path? Because the fact that they're added to the path in Linux allows you to just call it by name. If it wasn't added to the path, you'd have to go user, bin, whatever, and tell it exactly where it is. Yeah. So he says he's just going to try booting into Ubuntu and try it again, which, I mean, that should work perfectly. I use the Windows Linux subsystem, so I'm actually running Windows 10 right now, but they have that cool feature where it basically installs Ubuntu underneath it. And that's what I'm using right here, but I've also done this on a pure Ubuntu virtual machine before, and it works just fine. Don't save that. Don't worry about that. Okay, where was I? So while he tries that, we'll keep on keeping on right here. Okay, so what was I doing? So we need to add. Yes. So we want to. So in the case where both neighbors are free, we actually want to be updating the previous neighbor because that's the one that's going to survive. So we're going to wipe out ourselves, the current header we're on, and the next neighbor down. So we actually want to edit everything up in the previous header. So his payload size now equals the next payload size plus another let's see, plus, so the downstream neighbor size plus we'll get our own size plus 2 times a header size because we're eliminating 2 headers. Right? Okay. So we already know the merge down works, so we're taking ourselves and just changing our own size. The merge up neighbor is where the previous header is the one that's going to survive, and the current one we're on is going to be overwritten. So we want to be editing the... Oh, we want to be editing previous payload size again. Right here. Previous... equals just our current. Yes. And then in this case, both of them. Okay, so let's build that and see what happens. Okay, so it didn't break. Well, it didn't break because we didn't actually get into either of those cases. So, first of all, I'm going to get rid of this. So now we need to force a situation where we need either one of these other 2 cases. So we just proved that the merge down works. So now in kernel here, we gotta force a... So we could put number 2 back in, and then free number 2. That should force a merge across. So where we allocate one, we allocate another, we free the first one, there's nothing to merge with because it's just a free, use free. But then when we free number 2, we should merge both because we are now surrounded by freed blocks. So now we should see a merge across, hopefully. There we go. So right here we see a stop 1 because we got in the check to see if anybody was available, but nobody was free to merge. So that's why we didn't do any merging. Because if we got into any of the cases where we actually did the merge, we would have seen a merge something. So down here we got a merge across. But now see, we are back to the actual size. So what happened is, here, let me show you. Tablet fell asleep. So in this scenario, we made the first block right here, and then we made a second block after that. So now we have three blocks. So we've got, this is num 1, this is number 2. So So we made number 1, he's being used. Then we made number 2, he's being used. So then we freed number 1. So we said, okay, you're no longer being used. But he did the check to see if any of his neighbors were not being used. He doesn't have a back neighbor. And his only neighbor downward is being used. So we can't do any merging right there. And we didn't. Let me see if I can maneuver this so you can see. Yeah, so there wasn't any merging. It didn't say so. It did a check here. It got into stop 1, which does the check to see if it has neighbors. And he did. But he didn't do a merge. Then we freed number 2. And said, okay. Oops. Then, yeah, so we freed number 2, and then he looked at his neighbors, so this guy's not being used either, because that's the rest of the heap. He did a check on both sides to say, okay, is either one being used? That's why we see stop 1 and stop 2. Those indicate that there were merges, that there were free neighbors both sides. And then it did a merge across. So then we, instead of the point here and point here happening, we did that. And so now essentially this header is now gone. It's just lost in the memory, and it'll just be overwritten next time we start allocating away. Oh, one thing I think we do need to fix that I haven't done yet is we need to point these backwards the right direction too. Because when we were originally pointed like this, the previous headers were also doing this. So when we merge the pointers across to point here, we also need to go change these to say you're there, like that. And so that's also going to be done. Oh, this guy sent something back. I'm back in Ubuntu, though there is this error. Ah. He doesn't have the right cross-compiler created. So it's complaining that... Well, here, let me show you. Hold on. So see right here, it says this command's not found. That's the call to the actual GCC compiler that I made specially. So that means he hasn't made it yet. So he hasn't followed the tutorial on OS Dev. And I'm considering actually putting a script in the GitHub repo that people can run to actually just go fetch the tools and build them appropriately for them right there, so they don't have to follow the tutorial. They'll just do it. Yeah, you got to build it from source with some special settings. You have to tell it when you build it that you don't have any standard libraries or anything, because when you're booting like from nothing, you don't have access to standard libraries. Normally, when you build stuff, when you compile programs like in Linux, Linux has all the libraries and stuff for you that it can just give to you. Someone's calling me. I don't care. I don't know who you are. Yeah, so... It looks like his NASM problem was corrected, though, because the assembly files did turn into object files. Then it just got stuck on the GCC, on the CPP files, because it didn't have a compiler to use for them either. Okay. So we'll just let him stew on that for a while and see. Okay, where was I? Okay, yes. So we have to correctly update the linking backwards, too. And that's going to be done in the same location. So when we do a merge, we need to set the previous to something also. So we can go backwards. So it would be easiest after we've already erased the header between. Or maybe not. How do I want to do this? Let's do the simpler cases first. So in the simpler cases, the merge down case makes the most sense because the current header that we passed in to start with survives. So we need to go, let's do it before we obliterate the header in between. So there's a header here, and then we call next, which gets us to this guy, and then we call his next, which points to the one below it. So then we need to point the one below it back to us. So let's do that before we blow him away. So we need to do current header next, which gets us to the one after that. Previous. That's kind of confusing. But so that'll say our current header, the next one, his previous variable, which was pointing back to this guy, we need to change it to point back to our current location. So equals current header. Like that. And so that'll change the header even farther upstream, and then the next one will obliterate the one in the middle, actually, by pointing ourselves to it. So the one that was in the middle is now overlapped both ways and is now just lost in the data. Stop calling me, people. Someone left me a voicemail that I don't know who they are, so we're not going to worry about them. Okay, so that should be right. And then, so we got to do the, in the case where the previous header is the one that survives, and the current one we're on gets obliterated, we need to do the same thing we did down here, just kind of backed up one set. So we need to point this guy's previous to the actual previous. So we'll do that before we blow everything away. So we need to do current header previous. No. Next. Previous. So we'll start in our current, we'll go to the next guy, and then his previous field needs to equal current header. Oh, I got double equals in there. Current header previous. So we'll say, okay, this guy's previous field needs to become what our current previous field was. So now it'll point to this guy, thus overlapping current and obliterating it completely. And then this one is going to be the doozy one. So now we need to do, we need to set this guy's next previous field to all the way over to this guy. So this is good. This is going to get long. So current header. Oh. Next. Oh gosh. Next. Previous. Now equals current header previous. So that's saying, all right, current header next. Let's actually make another one right here. So it's, let me make another little box here. It's gonna be bigger too. So. This is next. Next. Like this. Yes. So current header next next. So current header next next. This guy's previous location needs to point all the way back to previous. And so we set his previous field equal to what our current header previous was. So now both of these blocks should be completely obliterated. Yeah, so current header next next equals the previous, and then the current header previous equals next next. So previous is going to point all the way over here to next next, and next next is going to point all the way back to previous. These guys are back yet? No. I'm really curious if that guy can build it, because I'd really like to know, or it'd be really cool if someone actually was able to build it. And that should be that. So let me build, make sure we didn't break anything. Didn't break anything. That's good. Okay, we still haven't tested a merge up yet, though. So we've tested the merge down and the merge across. So now we need to force into a situation... Oh, and that's a really simple thing to do. We just need to allocate one more variable between it. So number 3 equals malloc. And we got to be big enough to where... Let's do like 120. Make it nice and big. And then eventually free number 3. So we might get two cases here. We should get a merge. We should actually get a merge up and a merge across in this case. Perfect. Look at that. So we have a merge up and a merge across. So this time we allocate number 1, we allocate number 2, and we allocate number 3, and then we have the rest of the heap. So we have 3 allocated variables. So then we free number 1, he's got nowhere to merge. Then we free number 2, he's only got one free neighbor, which is number 1 above him. So we do a merge up, and now we have one big free block there. And then we merge number 3, which has free blocks on both sides, so then we get a merge across, and then we get right back to our original heap size. That's pretty sick. Okay, so I'm going to get rid of those stop variables, because those seem to be working fine, or this right here. Because that was just telling us whether or not neighbors could be seen. And now that I'm certain they can. We don't need them anymore. Yeah. Okay, so now that the number seems to be working out correctly, I don't think I needed to print all that number too. I think let's see. I think I put those in debug. Yeah, so I've got a debug if def in here. So if I just kill that, yep, there we go. See, so now we've just got merge up and a merge across, which makes perfect sense. So now let me just try I guess maybe I'll just try throwing a few more out there. Void. Oh, let's try this. So number 4 equals malloc. Let's try 40. So essentially what that will do is that will actually reuse block number 1, theoretically. Because block 1 is less than the minimum size, so it becomes 64. And then we free it, but he had nowhere to merge. So there's just that blank 64-byte block still there. So then if we do another allocate of less than the minimum size, this guy should fit into the block that was block number 1. So then when we get to freeing block 2, his previous neighbor should not be free. So he won't have anywhere to merge. So we'll lose that merge up that we saw. But then when we free block number 3, we should see a merge down. No, we should see a merge across at that point. Because, yeah, we should still see a merge across. So we should lose the merge up that we saw. Unused variable, blah, 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 blah. Okay, so if I free it, this should be a merge down. Because this should merge with the rest of the heap that's below us. Yeah, look at that. So we see a merge across and a merge down. So that first merge up between block number 1 and number 2 no longer happened, because when we tried to free number 2, the spot that number 1 had originally was reused. So it's not free anymore, so it couldn't do a merge. But then we freed number 3, and number 3 is adjacent to number 2, so they merged. And then we freed number 4, which is adjacent to the big block of 3 and 2 and the rest of the heap, so then it merged both of those together back into one big block, and we got back to everything. Just for fun, after putting that in, I'm going to put that number back on. Or have those numbers show back on to make sure we get back out to the heap size we expect. Which we do. Look at that. 16370. That is so cool. So at this point, we have what's called bubbled memory, is where it sections off the pieces and then tries to merge them back together as it can, like kind of like bubbles combining together to make a bigger spot. And so theoretically, as stuff gets freed and merged, we can keep reusing the same section of the heap, and we don't have to extend all the way down by keep adding new spots. Because eventually, we had the mechanics to split blocks, and eventually they would all get split down so far into really non-usable pieces. So the ability to crunch them back together again to make bigger pieces that can be reused is really gonna up efficiency in a lot of ways. Okay. I think I'm gonna go ahead and surround these statements in debugs also. Okay, that's so sweet though. So, what is the next logical thing to do from here? So, again, another thing that I've been dreading is activating what's called paging. Which is virtual memory. Which sounds really, really hairy. But it can use a similar concept as to what I've just made. It can use another kind of linked list idea. But I don't really want to do that right now. Let's go ahead and commit some of this right now, actually. Let's add both of those because they're both referring to the same thing. Oh gosh. Add everything. Get... Let's see. Malloc. Free. Got the block merging working. Yay! Sweet. This guy on Discord hasn't gotten back to me yet. Oh, it says he's not online at the moment. Okay. What do I want to do now? So what I would like to do, I did mention earlier at the beginning that I would like to try and see if I could get a serial port debugging working. So Kimu, which is my emulator. It's still going to run all that, that's fine. So Kimu is a hardware, it's a processor emulator essentially. So it presents some devices as hardware that you can use. Like one of them is the screen, for example. It's actually doing the VGA screen for me, or pretending that there's one there for me to use, which is why it's actually printing anything. But it also presents some other stuff, like it presents serial ports. And so I would like to figure out if there's a way, or figure out how to write to one of those serial ports, so I don't actually have to write data to the screen. I can just write data to the serial port, and I believe it will actually pop out in the PowerShell that I'm running Kimu from. And in the PowerShell, you can scroll up and down. Like in mine here, you can't scroll. So like if something gets pushed off the screen, it's gone forever. So I think it'd be a really cool thing to be able to put stuff, only debug-based stuff, to the debug terminal, and don't have to have debug statements out the wazoo on the actual screen output. So I think that'd be a really reasonable thing to try and do. I'm going to be right back, though, okay? Give me a few minutes. Okay, I'm back. I'm getting kind of hungry, so I had to go grab some stuff to snack on. Cheez-Its for the win. Okay. So now, I've been working on this memory feature for a long time, but now that it's finished, I actually need to go do some research now. To see exactly what, how to get serial output from Kimu. Alright, so I have to get serial out of Kimu. How to set up Kimu output console. Let's go to OS Dev. I'm sure there's a port or something that I can write data to. Yeah. You guys can see with me. We want, Kimu console. Okay, so this is about Kimu. So these are all the video. These are all the video modes it can access, I believe. These are all the supported architectures that it can use, and these are the devices that it simulates and presents to you that you can use. So I think what I need to figure out is how to write stuff out to a serial port. Oh, sorry. Bumping stuff around, shaky. Serial port. Okay. Boom, here. So I can access them better. So, there's an interrupt that will fire. I do know that there's an interrupt that will fire. Oh, hey, Omobu. I didn't see you come in. Yeah, that's what I'm trying to do. I'm trying to see if there's a way that I can... Yeah. I'm trying to figure out a way to write data out into Kimu's serial ports for debug purposes. Because right now, all I'm doing is just dumping crap to the screen. and there's no scrolling. So if it gets pushed off the screen, it's gone. So what I would like to see if is possible, Kimu's getting run out of a PowerShell, actually. And I'm wondering if there's a way I can feed data from here out into Kimu's standard out, which can be put into the PowerShell. I've seen that done before. Or something like it. So that's why I'm just kind of reading up on serial ports right now. Because I know that there is an interrupt that will fire when there's data ready to be read on a serial port. Just what's the port? This is about serial in general. Serial port. Let's go back. Oh, is this the same thing? IRQ. Actually, let's go back to the IRQ. Hello, Wobotech. Yeah, so I was looking at that. That's a flag for Kimu. I believe that's how you dump data from Kimu into the shell that's being run in, but I need to get data out of my software into Kimu to push out. Know what I'm saying? So I think you're right. I think that serial studio flag, or standard IO flag, will be step 2. I just got to figure out how to write data out of my kernel to Kimu's serial hardware. And then I believe you're right. It should just be a matter of redirecting that to the console that I'm in. That would need to go through the virtualized... Yes, that's what I'm saying. Kimu is the virtualized CPU. So it's presenting me with the serial device, if I understand correctly. So I just got to figure out where to put data so that device will capture it. So way back when I was putting keyboard support in, let's see, it's got to be somewhere. Way back when I was putting IDT in and trying to get keyboard interrupts working, there's also interrupts for 2 serial devices. What? Oh. Interesting. So this is the hardware that is being presented. Hopefully this isn't like a very bad site or something like that. Okay. So this is datasheet. Does it? Let's see, look at the top here, just out of curiosity. Blah, blah, blah. So this is the device that it's emulating to provide serial data. So this is timing crap. We don't need that. Don't need that. Don't need all that. Address register. Okay, this is more about the device, though. That doesn't really say how the device is hooked up to the CPU. Because I need to put it out the door, the CPU, down to this device. So I just need to know where the door is, I suppose. Sit back. was the... I know it was talking about... pipe the output to the host terminal. Well, that's exactly what I'm saying. So, like, the VGA that I'm doing, I'm drawing directly to a location in memory that represents VGA screen data. So what I would be able to do from a software perspective is just change in software. Yes, change the direction where I'm writing stuff to. Instead of writing to my screen memory location, write to wherever that serial port out is. I just gotta find out where that is. Interrupts. I know I was talking about it back in the interrupts area. Yeah, so I just gotta know where to, like, software-wise, it's not that, it wouldn't be that hard to just direct it somewhere else. I just gotta figure out where I need to put it, so Kimu, as a program, can dump it somewhere else for me to see. Yeah, so here. So these are standard IRQs. There is a COM1 and COM2 capability, and I believe that's what I need to do. But it doesn't really give me... What's this? Ah. No, that's a stub. Let me just try, like, X. I mean, sorry this isn't super, super interesting, but... Basics, COM ports. IO ports. Ah, here we go. This is a nice looking list. IO ports. I need to save this off. This would be a good thing for me to save off. It says right here, if you're an OS developer, you should not be looking for this. Okay. Right. Well, it's telling me something here. I need to do something about this. Okay, so here we go. So yeah, so there's the PIT. I've used that one before. The pick, I've used this one before. There's the second pick. I've used that one before. Serial ports. Here we go. So these are the locations of the first serial ports. That's all fine and dandy. Okay, so I guess I should go ahead and lay some groundwork in first, so I guess I'll go ahead and make some new files. Let's see, a new file. Serial port.h. Def. Standard stuff. That. And then in my source, I really need to organize this into something. But my make file is so tightly wound and works so well that I don't want to move anything around. Serial port.cpp. Let's see, so we're gonna have to include standard IO and include serial port.h, whatever that ends up being. I don't know. So, okay. So in here, I like. Does this take me somewhere? Okay, this is good. So I like saving off these port addresses as nice enums, so they're easier to understand. Yeah, so the external logging, this is what I'm interested in. The ability to do external logging. Okay. Let's go ahead and define some of those into a nice enum. Serial port keywords. Com1 equals OX EF8. Com2. I don't even know if I'll need all these. There's evidently 2 like serial ports you can use, and each one uses 2 of these ports. So I don't even know if I'll need both of them, but I mean, I might as well go ahead and 8 com3 equals OX 3E8 com4 equals OX 2E8. Okay. Those are nice and good to use. Okay, you might want to find... So, alright, so once you have the base address of a COM port, oh, it looks like there are 4 actually. So there are 4 devices. So these here are the offsets to get different stuff inside each one of these COM ports. So if I just wanted to stick with COM1, it says +0, which meaning this actual address that I have. That's how you read. We'll read from the receivers, but we'll read from the receive buffer, and writing to it will write to the transmit buffer. Okay, so that's pretty easy. Interrupt enable register. Oh. Looks like it could be useful. We'll see. Might already input. You know, so let's take a look here and see. Software, we get down to use. I'm using a virtual machine, so I'm not going to worry about that. So there's an IRQ for when data gets, or when data is present. So because I only plan on writing out this thing, maybe I don't even need to bother doing that. That'd be fantastic. See, because there's an interrupt enable register. So what I'm guessing is, by writing this guy, or allowing this, that will allow the serial device to fire an interrupt whenever it gets data. So I don't think I actually need that if I just want to write out it. I don't really care if data comes back in. Parity, I don't really care about that. Yeah, see, so the interrupt enable register, it tells you if there's data available to read or if the transmitter's empty. Huh. Is this it? So what is this doing exactly? So it's writing out, so disable. Oh, you gotta set a baud rate. Oh, I might need... Maybe it won't be able to go to the actual terminal like I want, but I still could always run like a Minicom or something and maybe connect to it that way. Unless that standard I/O flag is just smart enough to dump everything to standard I/O, then it would be that simple. Do I really need to do all this? Because I don't plan on reading from it. Is transmit empty? Oh, I see. So you do want to make sure that, because you can only apparently transmit 1 byte at a time, you do want to make sure that transmit is in fact empty before writing another byte to it. Okay, so I mean, it looks like a lot of this I'll have to go ahead and just do. But that's okay. Alright, so we'll just do something kind of similar, I suppose. So normally I like... Excuse me. Nope, let's kill that. I like doing a... Man, things in my throat. An install function is what I like to do normally. So... What do I always call them? So, yeah, so pick install, so we'll do... serial install. I don't think it'll need to take anything because we'll only use 1 serial port, I suppose. So in here we do need to include standard I/O because that has our... Oh wait, no, I don't want to define that in here. Darn. Nope. Don't do that. You don't need that. I want to do that in serial port CPP. I don't know why you're complaining, whatever. Okay. So, in... let's see. Serial install. I guess I should probably just do a lot of this same kind of stuff, so... And I saved those off as com1, so I guess we'll do out byte com1. That's all we'll do at this point, I suppose. Right, so if I were to just read or put anything right there, just into com1, that would write it to the transmit buffer, but I have to set up these bits and stuff first. So we need to go, yeah, +1. 00, that says it disables interrupts. Yep. That would be com1 +2. So you have to set the baud rate and then a baud rate divisor. What is... DLAB set to 1. This is the least significant byte in the divisor. mean, to be honest, I don't really care so much how this works. I just rather it works so I don't... I'm not super interested in how this is actually working, to be honest. I just kind of want it to work to help me later. So, till eventually I don't need it anymore. Oh! I didn't even think about that. The one in 1X. Let me go take a look at that. I was looking at that repo a little while ago, actually. Or I've been looking at it. It's really good. I like it. It is pretty simple. Where's X? Oh, really? Maybe I should, Oh. Why can I not find it all of a sudden? X1. Oh, there it is. Okay. So. Blah, 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 blah. UArt. Here we go. Oh, gosh. Oh, gosh. No. Okay. So, this is what X1 is using. Maybe it would be in my best interest to go ahead and set up being able to receive from it also. I don't know. While I'm already dealing with this. Sanox. Write that down so I can... go look at his channel eventually and see. Okay. So he sets the baud rate, yeah. He sets a clock. So he does divide by and gets 1. Okay, whatever. And then he just creates these offsets. So that's like what I was doing right here by doing adding up here. He's just defining what they all are ahead of time right here, looks like. What? So, I mean, one tomato, tomato, whatever. Data share between threads and the interrupt handler. I don't have threads yet, so I don't really know if I need to go quite so hardcore. Yeah, so the UArt setup, this is what I want to look at right here. So he initializes a buffer. That's this guy right here. UR buffer of size 16. Yeah, so he does something really simple, really similar. And what are these down here? So, yeah, so this is for reading. Don't really know if I need to put in reading at this point. Yeah, so he registers an IRQ. You know, it's probably not that difficult to just put it in, so I guess I'll go ahead and put in both. Alright, so what exactly is he doing here? Plus port reg. That's the problem with people who are overzealous in their defining of stuff. You gotta... So UArt reg LCR, that's the +3. UART reg div low and div high are 0 and 1. Okay, so that makes some sense. So I like the way the example on OS Dev was doing it though, so I guess I'll just do what's the baud rate that it comes out to be though? Because this one looks like it does some math. Because it sets the divisor to 3. Well, let's just bang it out and see if see if it works. Plus 0, so that's the actual location of the port. So 3. That would be that would be 1 plus 1 again. It's just 0. Plus 3, that's setting up parity bit, the parity bits, and that's evidently sets none. Plus 2, enabling a FIFO, I suppose. That's what it says. That'd be COM1 plus 4. Oh. Okay. Gosh dang it. Okay. Okay, then I guess I'll go ahead and register an IRQ, I suppose. Can't hurt. How does he do it? UART IRQ and gives it the UART IRQ handler. Okay, so what number is IRQ? 4. Okay, no big deal. How do I register my IRQs? So I think I need... Mine's not 0 based like his is, so mine's actually continuing on from the interrupts. So timer actually is number 1. Keyboard's 3, I think. So I believe this is just going to be 34. Ah, no, I'm paranoid. Oh, timer is 0, so 0, 3, 4, 5, 6, 36. I think. Register interrupt handler is undefined. What did I include here? ISR helper. Did I also have to include some other stuff? No, that's everything. Okay, so then I gotta give it a callback. How did he do it? Not sure why he has another parameter right there, but that's okay. I don't care. So where's IRQ handler? It's right here. Yeah, so this is only handled for reading. He only does reading in the IRQ, so that's fine. So I guess I'll go ahead and just do I'll call port, call back, and just make it a no op for right now. To do yeah, I don't need to do anything with it, but I mean, it makes some sense to maybe put in the plumbing for it right now while I'm already here. You know, maybe I want to use it later. I don't know. We'll see. I'm trying to learn some good system development habits, and that sort of thing is one of them. Okay, so that's that. Then, what's going on here? So we just have a lovely little read and write. So I guess we'll go ahead and just make a well, so it checks first to see if the transmit port is empty. That makes some sense to do, I suppose. Check TX empty. And it just reads in a number, so return inb com1 plus 5, this location. And just does a bitwise with 1. So, I mean, they just check if nothing is being transmitted at the moment. Makes sense? And then in the actual write char serial, the actual character. Gosh. Oh, I see. And then it's just it sits on a while loop. Check TX is empty equals 0. So if it's not empty at the moment, we'll sit there. Sit here until TX buffer is empty. Out B, com1 C. What are you complaining about? Oh, there we go. So, I mean, I guess that's that. So now, the only thing is, the only way I can really test it is if I can get Kimu to pop it out, so I don't really know if there's a way to... Oh, it's that flag. So let me try throwing that flag onto, just for fun, see what happens. So on my run Kimu bat. Serial STIO. Right? Oh, we gotta use this somewhere too. We have to install it first of all. So, oh wait, serial install is supposed to go in sys. Is it sys? Syslib? Yeah, it is. Extern void serial install. Okay. And because it's just setting some bytes around, not doing anything interesting, we can do it pretty early on. So let's do it like up here maybe. Set up serial port. Right there maybe. The things that are literally just writing out some bytes to places that don't really require anything, they can be done really early. So to be honest, like this could actually probably be done like this, the pick, and the timer. That's a good idea. And you know, I think it can actually be thrown out like much sooner because it doesn't need. It's just reading and writing stuff from a location. To read from it, yes, pick has to happen. Oh, I see what you're saying. Yeah, for it to actually make any sense. So on the other hand, though, I'm pretty sure pick can be done. Well, if we're if we only need interrupts to read from it, though, then it can be done before ISR and IDT. If we plan on reading stuff, it has to be done after ISR and IDT because it requires an interrupt. But theoretically, just to write to it, it could go earlier. Before registering the IRQ. The pick is not technically, but if an IRQ happens before we reinstall the pick, then it won't work. Because the reinstalling the pick is what remaps it. So I could set the IRQ number correctly, but before the pick is installed, it's wrong. So it's only where is it? This number here is only correct after pick gets installed. Right, so for writing out to it only, like this stuff right here helps set it up, and then just this right here puts data onto it. So it doesn't need anything special. So let's try putting it up a few notches. I think technically we could actually put it at the beginning because it doesn't rely on needing like privileges to do stuff with. It's pretty sure it can be like. We'll see. And then move the pick or the serial. I meant to move serial. Oh, whoops. Good catch, thank you. Blah, 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 blah. Serial. There we go. But you know, I mean, pick, theoretically, could go a lot earlier, too. I need to work this out. I'm not going to bother with it right now, but I'm sure there's an optimized something or other. Alright, so where was I exactly? So let's get rid of that. Let's get rid of that right now. The dependency graph, yeah. I should go through and make one of those. You know? That'd be a great thing to have. Okay, so why are you not happy? Oh. But that's defined actually elsewhere, so it doesn't actually matter. My install function is in my syslib H file. So that should be fine. And then I would likely want to put my reading functionality into my standard I/O location, probably. So, extern void write serial char. These all take const char pointers. I'll have to make like a print string to serial string function, because right now, yeah, so the way I did it here, oh gosh, it can only do one char at a time, but if I do it kind of like the way printf you did it, I could take a pointer to the beginning of a string and just print until I hit a null terminator. Yeah, so const char. Well, yeah, so I mean, like, I'll use this print write char serial correctly, but, well, here, let me just go ahead and do that then. So void write. This is the function that'll be exposed to everybody to use. What did I call it? Let's... And then we'll do a while C does not equal a null terminator. Oh gosh. Write char serial C. Boy, oh, right. Like that, because this is an actual. This is an actual char, so we gotta. This is a pointer, so we gotta give it the thing that it's actually referencing. Yep, you're right. And print the same character over and over again. Forever. Okay, so this is what is exposed to everybody. So, I wonder if that's that. Let's make a new, let's get rid of the malloc test. I mean, theoretically, if I get this working, I won't need these defines anymore to turn stuff on and off. Because that was the whole point, because I was printing a whole bunch of crap to the screen. Oh yeah? What's that? Oh, the write char function? Yeah, I never got around to fixing that, actually. I think I have an idea how to, but I never actually got around to doing it. Hello. My VGA writing code is not pretty anyway. I kind of want to just redo it from scratch at some point anyway, but so, I mean, I changed, yeah, save that, right? That's the script that runs it. What could go wrong? Forbids comparison between a pointer. Oh, derp. Derp, derp, derp. I need to actually... Right. There we go. And we are stuck. Where? At right here. Well, wait a second. I don't think I'm actually printing anything at that. Well, no, I've got done printing down here, so that means it is stuck. Well, I mean, Kimu ran still with the new flag, but it doesn't look like it did anything. Alright, so where are we getting stuck at? I've got standard Oh, don't I? I can't. I could just for fun, print char C, right? Because that's a pointer. Okay, so it got in here, and... Oh, it's probably sitting forever on this while loop. Ah, crud, I can't print this, though, because this is an actual literal character, and this takes a pointer. Yeah, that's why print char isn't that great. Unix only is standard output? Crap. Ah, dang it, I'm not running Kimu from Linux. Fudge. It's kind of a weird process, actually. I'm doing the building and all that with the Windows Linux subsystem, but since I don't actually have Kimu installed in the Linux part, I've got it installed on Windows, but my... Oh, really? So, you mean like... Where's my makefile? Nope, that's... Let's take a look at that. 2311. X5. Okay, cool. Serial. File name. Looks simple enough. Okay. So my makefile here. Let me show you. So under my .run or my run recipe, I've actually got it starting a PowerShell and feeding it this script, which is this this batch file script up here, which actually runs file serial out. Yeah, it's pretty neat. It's such a hack workaround too. Yeah. No, yeah, it's hacky as all get out. Like, my entire makefile is just one big hack. It's so funny. But as you see, like, sometimes I do actually do this on a actual Linux machine. So when I check it out onto a Linux machine, I've got another one here that just I switch it to, and it just literally runs Kimu as a program. Okay, so we've got serial. Do I have to like quote it and put it in quotes or anything? Maybe not. Doesn't look like it. How to put it to a TCP? Wow, that's kind of cool. Okay. Oh, we're still stuck on that. We're still stuck on that loop, though. We didn't fix that. So, wait. I can... I can use printf, though. Well, actually, here, let me... Well, no, I don't need to do that. I'm almost certain that we're getting stuck here. Well, no, actually, let me go and do a printf just to prove that we're... Hello. Just to prove that's where we're getting stuck. Yeah. Oh, you're right, it does. Yeah. Yeah, I think I figured that out early on, but all these I didn't actually bother to... Yeah, I don't actually need these. Yeah, like I didn't put it on this one because I figured it out, but yeah, you're right. So I must not be... No. Equals... Let's move this up here. Decimal in num. I just want to see it should be stuck 0 if I'm stuck where I think I am. Boink. Yep. So this is never coming back. So it's got to be something that I'm doing. Did I not do this right up here? I might not have done that setup step correctly. So let me see here. So 1 is 0, 0, 3 is 80, O is 3, 1 is 0, 0, 3 is 3, 2 is C7, 4 is 8. Oh wow, it's O 0. What are you talking about here? Define UART. TX empty is 20. Okay, so then what does he do with that? So he reads in from the port plus UART reg LSR. Which one is that? UART reg LSR. That's plus 5. Which I'm doing right here. See? So that's the same spot. And then it's anding with a... Where'd it go? Ending with bite. Oh, darn. Okay. Yeah, so he's reading from that spot, which is what I'm doing right here. And then ending it with is... You are empty, which is what you wrote there, which is 2-0. So, I mean, I'm just checking that it's not 0, so I don't really care what it is. I'm just caring what it's not. Which flag did I care which flag is set. Up here? Now it's still 0. Oh, if I set the right bit. Yeah. Well, we didn't hang. We printed the same... Oh, it's because I got it printing, Oh, because I got it printing a number. Oh, well, let's go. Did we write something? Yeah, let's... Did we write anything, actually? Where would it have... I believe it would have been up here in the scripts file, because that's where Kimu's actually being run from. And it doesn't look like it dumped anything. It would have ended up in here, I think. Yeah, serial file, serial... No? Am I wrong? Oh, is it way back up in my... Oh. Yeah, it'd be where I installed Kimu at, wouldn't it be? So that'd be up in my... Where did I put it? I think I put it in install programs. Hey, look at that! No way! Look at that! Woohoo! You're right. Okay, so why don't I... Can I pass it like a variable or something to like... I mean, I could just give it a That's a good point. That's a good point though. So, because we weren't even sure that was working. So, std in, right? Yep, my bad. Out. Yeah, Kimu crashed because it probably didn't recognize that. And it's still stopping. Oh, man. I should really learn to read sometimes, you know? Look at that crap right there. That is fandangtastic. All right. Okay, cool. So, to wrap that a little bit... Yeah, that's freaking amazing. So now, I'll never have to worry about losing losing data anymore. So what I should do now is make a nice way to redirect that. I'd like to do... See, so printf relies on print char, which prints directly to screen memory. Just for fun. I want to see what happens, like, if. What if? Instead of... Let's see, that's going to be in print CPP, I believe. Yeah, so here's... Hardy Onyx. Welcome to the stream. Thanks for the follow. Instead of this, what if I just write everything... Write serial string... Now that takes in an action. Oh, can I just do traverse? See if that prints everything to the console. I'm just curious. Oh, goodness gracious. Exceptions out the wazoo. Well, I hit it. Oh, wow. Oh, sorry. I'm dragging the wrong thing. That sure didn't work. One char at a time. Well, it's... Print char just takes a... Oh, you might be right. Is traverse actually a... Traverse is a char pointer. I mean, write serial string just takes a const char pointer, which is what traverse is, which is what print char was doing. What happens if I put them both in there? If I... That'll just cause everything to go both places. Yeah, it's not happy. I mean... Yeah, that's the problem. I mean, I didn't look at any documentation or anything for what it's supposed to be when I made it originally, but... Yeah, okay, so let me get rid of that that print, that crap right there. Printf use write serial char function. Yeah, that's exactly what I did right there. This is my printf function. And it relies on print char, which takes one char and just pops it in. Well, therein lies the problem. Right now, write serial char takes an actual char. Oh, well, I could just feed it the... I could just feed it the dereference char. Oh, shoot. Okay, so for example purposes, I will have to add this to standard IO, I believe. And void... Yeah, so this guy just takes a char. So now this guy will be acceptable here, so then we want traverse bet. Oh. There we go. Ha! Ha 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 ha. That's so cool. Oh, that's neat. You have an idea? Please share. Because to be honest, now would be the time to do this. Because right now, printf is reliant on print char, which is defined specifically to print to VGA memory. Actually, it should probably be print char that is generalized, right? Wouldn't you say? Rename it to something like fprintf. Have its first parameter to be a function pointer to avoid. Oh, and then depending on which one you want to use, you can change that function pointer? That you have printf, call fprintf. Yeah, that's a good idea, because I do want to keep the formatting functionality of printf available to use in many places. Let me read that again. So, rename something. So the one that I use, like, out and about, would be the one where you pick if you want serial or screen. Is that what you're saying? The function pointer to avoid. This is the point where I really need to really need to work on like a standard I/O kind of idea, but rename something like fprintf. So you mean kill this. So you mean this stays the same, but I make another one called fprintf that then calls this. What do you mean by have printf call fprintf? Fprintf calls printf. Oh, is that what that means? Flexible printf. Interesting. Prints to a file descriptor. Oh, file printf? That makes sense too. Someone must have spent some time thinking about that. Oh, okay. So printf is still the one that everyone uses, but you can use fprintf if you want to go somewhere different. Oh, okay, I see. So if I want to print to the screen, I can just make printf. I think I see what you're saying. I think I see what you are saying. So fprintf should have all this fun stuff inside it, right? So that's fprintf, and you said give it a. Can it just be a void pointer? Is that how you pass a function pointer? Yeah. No, it's not. What did you say earlier? Is that like what you typed? Kind of like that? Because you have to give it like a parameter that it's going to use. Oh. An actual... Well, it doesn't like that. Seems to be okay with that. What do I call it? FP? FD. Const char pointer. Oh, I said it's going to take a regular char. Yeah. So I will have to change print char to use an actual char rather than a pointer. That should be pretty easy though, because print char is like last in the chain. It's like that, and then really? did I have it broken that bad? Print until null. Does it? Yeah, it does. Like I said, this is not pretty. This is not... I should probably just read... I should probably redo this, to be honest. I made most of this up. You're not sure how it was actually working? Why is that? Mm-hmm. It's been working this whole time since I made it. Oh. Well, yeah, but that's just because I put them right next to each other. This else isn't the common case. It's not. Never called print until null. Why did I have it calling this? Was this supposed to be like a recursive? No. How did I have this working? Wow, I can't really remember. This is bad. This is very bad. Yeah. Yeah, it just goes until the end. Oh, and then in all of these cases where I use it, give it a long too. That sounds really ugly though. I don't even remember why I needed to do this, though, because look what I'm doing here with the decimal and the negative sign. Like, I'm using it to print one character. Yes, it is very silly, I agree. What was I doing back then? Why could I not just print... Oh, I see what I was doing. So in my... This function here is what turns... It converts bases. That's how I have it do things like hex and decimal and all that fun stuff. So that's why... This? This is all terrifying at this point. Why is it so terrifying? Huh. It's returning the... Wow, I should really have it return like an actual char, shouldn't I? Would it be so bad if I just made this do an actual char? No, you're right, that would not work. It doesn't have to be anymore, though. Oh, I see. So... So it makes the pointer, or it places the actual character in the stack, returns a pointer to it, and then wherever it jumped back to, but eventually that pointer could be overrun because it's in the stack. Right? So it's not really needed anymore when it comes out there, so it's not a big deal if it gets overwritten. But I see your point. Yeah, that's what I'm saying. If... Okay, yeah, you're right. Make other fun. Yeah, no, you're right. So you're saying it'd be better if I had a representation? What does that mean? Like the fact that I'm dumping stuff to the screen right away so it doesn't matter anymore? I make a function call, it'll overwrite that first. Are you talking about like the way the stack ends up being? Okay. Oh, that's true. You're absolutely right. Yeah, I didn't even notice that either because I did that purposely with other things, like the timer is static. I'm pretty sure, and I'm pretty sure I made the stack static or the heap static also. Doesn't that mean it's... No, it's inside a function that the value gets retained. Where was I doing that at? I was doing that, Yeah, so, like, I did this with my time data struct. But, I mean, I could put that... I could theoretically put that into, like, my install, though, couldn't I? That doesn't need to live out here. Internal to this file. Because that might actually solve a problem, then. Oh, well, if I then put this like into my install somewhere, then theoretically I'd be able to get it like from the kernel, shouldn't I? If I made it available by reference somehow. Because that was a problem I was having. I couldn't figure out a good way to get like the contents of this. Oh, really? Maybe I was just thinking about it wrong. Because I wanted a way to... I wanted a way to get this. Yeah, I feel like I tried something like that, but it wasn't working. Oh, hang on a second. text message. Spell, gosh dang it. Okay. In fact, I should probably go ahead and commit some of this crap first of all. So change the view here. What? Get status. There we go. What did I change in standard IO? Okay, so I only want to do the serial port stuff right now, so get add kernel serial port source include standard IO source kernel implemented serial port I'm really directed anywhere, so oh wait, that also goes to shoot, I forgot about the key script. Add scripts. Standard IO to for serial. Oh, I also added to syslib, didn't I? Source. I'm still learning my way around Git, so I don't really know the smart ways to serial install serial function. Okay. This is going to be a bunch of commits. There's a way to, like, you can amend commits that you've, with new files and new text and crap, but I don't really know how to, the right way to just do it, yeah. I just end up with a bunch of little commits because I forget one file here and there, and I'm like, whatever. Tortoise Git. Yeah, I used it. Tortoise is pretty nice. I've used it a few times. Okay. So, I'll worry about time later. I can do that later. So I guess I really should figure out how the crap this is work. This should probably go next. Redo printf. So the fact that it's using this to print one character at a time is kind of silly. So I'm feeling like convert should not... Well, it's using a null terminated string. That's the whole point. So all the result of all of these come back as a null terminated string. That's why I have to use print until null just to do that piece. Right, okay, yeah, so is there a smarter way to piece them together, I suppose? Because everything that comes out of here, even if it's like one character long, has a null terminator at the end. So it's got to go through print until null to print out its contents. So really, printf is just printing a bunch of little strings one after another. Yeah, that's true. That's true. I mean, it'd be easier like if I had something that just concatenated strings together at null, maybe. So if like this print until null, if it just concatenated them at nulls, then I wouldn't have to do this in here. To do the concatenation within, yeah. So like this print until null, instead that could be concatenate at null. Converts buffer is already dangerous. This one? Yeah, I just picked that number. Well, that's just for one, like conversion though is the thing. That's if it's. That's if just what I'm converting ends up to be 50 characters. That doesn't mean I can't print 50 characters in total. So, like, the longest conversion I can do. FFF to base 2, yeah. I see what you're saying. $32 characters. Yeah, so I can't overflow because I'm taking an int. So like if I made print until null, if I changed it to like a concatenate till null, and I passed in the same buffer over and over again, and the new buffer I want it to append, it could remove, it could go to the, till it finds the null terminator at the end, remove that, and then paste on its new portion with a null terminator on the end, so it builds up a string. That way. And it could all be done inside here, inside of fprintf, couldn't it? That's the kicker, is the thing. So fprintf takes vargs. So it could be... It could be... yeah, don't want that approach is feasible. Okay. Hey, Blue Barn. Yeah, I did actually. Let me show you. Oh, that's not what I want. Mega. I don't know what I'm doing. Oh gosh, what did I do? Oh, I haven't done all this yet. Hold on. Let me get rid of that. Get rid of that. Oh. Let me just pull this out for right now. Blah, 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 blah. Yeah. So here's the output, and it does actually take keyboard characters, even though it's kind of buggy. But yes, I did actually have to go in and teach it what to do with characters whenever characters get hit. It is a kind of VirtualBox. It's a virtual machine. It's a program called Kimu. And hey, I got a raid. But yes, it is a virtual machine. It's a more developer-friendly virtual machine. So you can tweak it a lot better for developmental purposes. But you can run this kind of thing. I've tested this on VirtualBox before. Hey, Jelangstorf. Thanks, Chris Biscardi, for raiding. Hey, everybody. Yeah, so... yeah, so right now I'm just kind of doing a refactor. Yes, it absolutely is. I have ran this thing before in VirtualBox, though. Like, an actual emulator, or like a more production or mainstream. Yeah, every time I run that, it just boots it from... That's it booting. Yeah, the process to build an image that can be run on... Yeah, the process to build an image that you could run on, like, VirtualBox or burn onto a USB stick or something is a little bit tougher. I've done it a couple times, but it's just so much faster to use this one. Just way, way, way faster. For those of you guys who just got here, something I just put in was the ability to write to serial. So actually see this hello here? So this PowerShell is what's actually running the emulator, and I've piped the serial input of the emulator to the terminal, and see this hello right here? I'm actually writing that from the kernel. So now I can actually, instead of needing to write to the screen, I can actually write down to the terminal. Here, I did something a second ago that was kind of funny. Or it was kind of cool. Write everything to both places. Oh. I gotta rebuild. See, so there's the output. And then from the serial port, there's the serial port. So, it's the same thing. You know, yeah, the keyboard doesn't work because the keyboard, when I give keyboard input, it writes manually to the screen. But, you know, maybe I could fix it. Maybe I could get around that. See the install. What would I rate this project? This is the hardest and slowest going project I have ever worked on. Oh, look at that. You're right. There's an error. Mobo is correct. See, so install timer here at 1000 hertz. It's actually not printing. Right there. So that's a... Huh. Yeah, it's been really slow going. I've been working on this for... consistently, maybe for the past, I don't know, couple of months maybe. I started it sometime actually pretty early back in the year. You guys can actually go check out the GitHub. You're absolutely right. Mobo, I think you're exactly right. So just if I were to throw that in, where is it? If I were to throw the serial in right here also, then it would print that as well. And then regarding the keyboard, where's the... It's down here. So if I do write char serial temp 2, it should flush this out to the serial every time also. Char... Oh. Got it. There, and again lies the problem. So there's the... So what happens if I... Yeah, see? So now it's popping up in serial. That's pretty cool. That's really cool. I still don't know what the skipping problem is. Sometimes keys don't get registered. Backspace doesn't work yet either. I haven't put in backspace yet. That's running really fast now all of a sudden. Sometimes it seems to skip keys. Like right there, it skipped a few of my keys. But the beauty of this is I can scroll back now as the thing. The keyboard code? Right here? It's just a big switch case statement. Or do you mean down here? Where it actually prints it? The big switch case? Yeah, that's here. What about it? I know it's kind of ugly. Yeah, no, so I had someone... Yeah, it looks like a big pain, yeah. So it does... Oh, I do have shift working too, so it can discriminate between caps. So like capital A versus... That's what this is for. So it does know if shift has been pressed. But in theory, instead, I'd probably want to do something more like a function pointer to say if shift is pushed, go interpret with this function and a different table, and if shift is not pressed, go to a different table and interpret it that way. Yeah, so A, B... Yeah, see, you just skipped a character right there. B, C, D, E... Yeah, it's just the entire alphabet, spacebar works, and enter works, I believe. And shift. Yeah. So, I just got the serial working, and then the big thing that I was working on a lot recently was dynamic memory. that was a monster. Because when you're building and booting from scratch, you don't have any access to the C standard library. It doesn't exist. So you have to make it yourself. So therefore, the malloc and free commands don't exist. So you have to make those yourself. So if I actually turn on that test, I can show you. Oh, not run. I gotta build first. Ah. Just make it up, please. I didn't actually... Oh, dang it, I got rid of all the... Oh, I got rid of all the print statements, dang it. Well, so... This portion of code right here is exercising the custom malloc implementation and the free that I had to make. I got rid of all the... Oh, did I get rid of... Oh, I know how to turn it back on. I gotta turn on debugging in here. Right. Blah, 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 blah. Yeah. Oh yeah, see, there's the same problem again. So here's the serial output. I don't have the serial working for stuff that gets interpreted by printf. Or numbers that get interpreted. So it's actually not printing out the numbers, so that'd have to be a separate place. But see, it's running through a test to show how much memory there is before and after doing an allocation of a certain size. So it says we have this much before and after this allocation, then we have this much before and after this allocation, and then there's a free in there too. And so at the very end, we end up with the same amount of memory, so it means the whole allocating and freeing memory on the fly is working. Which is pretty dadgum cool. I think, anyway. And all this is available on GitHub. So all of you guys can go look at it if you want. What time is it? Might have to get off here in a little bit. I'm gonna go rock climbing with some of my friends in a few minutes. I think, is there anything else I can clean up here while I'm here? So this code here, this is kind of hacky temporary too. This is what catches keyboard presses, and it's just running in a infinite while loop at the end. So ideally, if and when I eventually get threads, different tasks working, this would be done in a separate thread, but I don't have that yet. So I think I do need to optimize my printf, so I'm gonna put that back. So what I was trying to do. So what I want to do right now, printf is hard coded to write to the screen. That's what I was changing right here. So this print char function is printing directly into screen memory. which I don't really want that. I want to be able to choose if I want to write to the screen or to the serial console that I just got working. All this code is actually pretty bad, too, to be honest. So what did I have? I had this in here. I renamed that fprintf. And then I'm going to have to make this take the file descriptor. So basically what I'm going to do, I'm going to make it so I can pass it a place to print stuff instead of just being hard-coded to the screen. And so now this would get changed too. You can't imagine. I mean, it started out a lot smaller. Like, it started out a lot smaller than this. Like this file that I'm working on right here. Well, not this one. Sorry, the VGA controller. Here. This is what actually does the printing to the screen. This was one of the first files that I got working, and it's quite disgusting actually. I need to I need to go through and read it out from scratch too. It's on there's a lovely website. It's on OSDev, the OSDev wiki. Yep. It's there. I know this. Thank you very much. I've been working pretty hard on it. A lot of just like the pre-setup stuff is really, really tough. Like, it's just setting up the processor to work correctly. Like, all these steps right here at the very beginning, it just runs through all of these. Like, these first 5 here are just setting up the processor to be able to do cool stuff in the end, and yeah, it's not the most enjoyable all the time, but it's worth it once you get it working. So I actually now want to do FD. Thing referenced. Can I just do FD? Function pointers. So what I want to be able to do is every time I call this fprintf is feed it a function pointer that I want it to use. So if I want it to print to the screen, all I have to do is feed it the printchar function. And if I want it to write to the serial terminal, I just have to feed it the writechar serial function. And it will write everything down to that location every time I call it. But I gotta get it in here, too. Oh, wait. It liked that. Did it get over that? Print until null. I need... Yeah, I need a null character in there. So now, can I just create a new printf and hard code it to use. It's gonna have all the same stuff. So now a new printf, and then just do f printf and feed it print char format. Is that gonna work? Too few arguments in function call. How do I... Oh, can I just do a void pointer? Like that? Oh, no, like that? Or do I have to do that? I think I'm gonna have to do some reading up on function pointers. Oh. FP or FB. FD. FD for file descriptor. I'm not going to commit this for right now because this is broken. This won't build. I don't want to commit anything that's broken. But, what have I been going for? Yeah, I've been going for a while. I think I'm going to have to go and call it for right now, guys. But, thank you guys all so much for watching me. It's a lot of fun when there's a lot of people talking around. So, if you want to look at my code or you want to mess around with it or try it, there's Melted Hyperion. Thanks for the follow, dude. Thanks, my boy. Well, if you guys want the code, there's links down below for my GitHub stuff, and you're welcome to look at it and play around with it. And I'll probably be streaming some tomorrow too. So if you guys want to come back and join, it'll always be a lot more fun. It's always more fun when there's more people. But yeah. So thanks for joining me. And I will see you guys all later. Have a good night, or morning, or whatever time it is for you. Okay, bye.